So for this question, we're asked to draw the root locus diagram. So our system just consists of a controller, K, and of course the root locus diagram is going to be plotting where the poles and zeros of our system move to as we vary what the number in here is, K. And this here is the plant or the system that we need to control's transfer function. So I'm going to follow through the steps that I did in the recap video for root locus. And the first step is to identify the open loop poles and zeros so that we can plot them on our diagram. So for that we need to know what our open loop transfer function is, and that's fairly easy to get off our system. So the open loop is when we're just considering what's on the top line, we're not considering what's in the feedback. So we're going to have just K outside of S plus 6 over S plus 2, S plus 4, S plus 9. So looking at this on the top line, that's where we're going to get our zeros. We're looking for values of S that will force the whole top line to go to 0. And that's going to happen when S is equal to -6. And the bottom line is what gives us the poles. Again, we're looking for values of S that force everything on the bottom line to be 0. So if S is equal to -2, this bracket goes to 0, so therefore the whole thing. If this here, S goes to -4, then we have the same situation. And here it happens if S goes to -9. So we've got 1, 0, and we've got 3 open loop poles. So I'm going to draw our root locus diagram over here. So let's set it up with our imaginary axis and our real axis. And we should be able to mark on what we've just identified. So zeros are going to get marked with an O or a circle on the diagram, and poles are going to get marked with an X. So we have poles at -2, -4, and -9, something out here, and the 0 was at -6. Alright, not super to scale, but anyway, we'll do it on Matlab at the end and you'll see the nice looking version. Alright, so that's step 1 done. So step 2 is to do the real axis line segments. And for this, what we need to do is look at our root locus diagram, and we're going to join together every second set of poles or zeros, whatever it might be, as we move from right to left. So starting over here on the right, the first thing that we hit on the real axis is this pole at -2, and we need to join it to whatever's next on the real axis. So that's going to mean that these two are joined together, and the root locus is between those points. We don't join the next set, so it's blank in here. We then hit the next one at -6, and we need to join it to the next pairing. Okay, and then there's nothing out here, so that's where it stops. So every second pair gets joined together. Alright, so that's been done. So the third thing we need to think about is infinite poles and zeros. Oops, sorry, and zeros, not at zeros. So from before, we found that we have one zero, okay, at -6. So the number of finite zeros is equal to 1. Here we found that we have 3 open loop poles. So the number of finite poles is equal to 3. So what we know is that the number of poles and zeros need to be balanced within our system, and that's because every pole needs to be joined to a 0 through the root locus. So in our case, since we have an unbalanced number, it means we're going to have to introduce 2 infinite zeros so that we've got 3 in total here and 3 in total here. So I've just noted that in. We need 2 infinite zeros, and if we take a look at our root locus diagram, we can see where they need to join to. So I said that every pole and zero needed to be connected. So between these two, we've already got a connection between a pole and a zero. Here though, we can see that we've got 2 poles joined to each other. So what we need to do is introduce these two infinite zeros so that these are then connected rather than to each other to these infinite zeros. So when we get a bit further and we look at the breakaway points, we know that we're going to have a breakaway essentially in this area such that we end up joining the poles to zeros. So let's mark that in. Cool. All right, so the next thing that we need to look at now is asymptotes. And we have two equations that we need to apply. The first one is for where it breaks, or crosses, I should say, the real axis. So this is the equation. Alright, so on the top line we have the sum of the finite poles and the sum of the finite zeros. So we can sub that in. We have finite poles at these three places, so it's going to be -2 plus -4 plus -9, minus, we need the finite zeros, which is -6. So it gets divided by the number of finite poles and zeros, and we work those out as well. We've written them down here. It's going to be 3 minus 1. So if you put this in a calculator, you find out that your asymptote is going to cross the real axis at -4.5. So the other thing we need to work out for the asymptotes is the angle that they're going to be at. So again, we have an equation for that. Alright, so what we can do is pick different values of k. K is supposed to be an integer, so you can actually pick any integer for it, but I think the easiest thing to do is to start at k is equal to 0 and keep increasing it by 1 until you start getting repeating angles. So let's start with k is equal to 1. Sorry, k is equal to 0, that's where I want to start. So if I substitute in k is 0, that goes away, and it's just going to be 1 times 180. So that's 180 on the top line. And the difference between the number of finite poles and zeros is the same as before. We're going to get 3 minus 1. So this ends up working out to 90 degrees. So let's increase k by 1, and we get k equals 1. Again, if we sub that into this equation, so this time we're going to get 2 by 1 plus 1, and 3 take 1 on the bottom line, and this works out to 270 degrees. So if you keep going, say you go k is equal to 2 now, what you're going to find is you end up with a repeating angle. So it's going to be the same as the 90 degree case. So once you start getting repeating angles, you know that you've found all the solutions that you need to for your asymptotes. And another way of thinking about it is the number of solutions that you're going to need is going to be equal to the number of infinite zeros or poles or whatever it is that you need to introduce into your system as well. So either way, you should end up with the same answers. So now we can go ahead and mark these onto our root locus diagram. So we know that the crossing is at -4.5, and then they need to be 90 and 270 degree asymptotes. So let's jump over here. So let's say that -4.5 is about here. So we can draw in, we know that it's a straight line asymptote that it wants to approach. And it's going to be measuring the angles. So it's 90 degrees as measured from the positive real axis. So 90 degrees around to here, and then 270 degrees brings us all the way down. So that's why we've ended up with a vertical line that's from the 90 degree asymptote, and you know, going downwards is from the 270 degree asymptote. Alright, so now what we need to do is work out where our root locus breaks out of this axis and subsequently then approaches our asymptote line that we've just drawn. So that's step 5. So again, we have an equation for this. So Zi and Pi, they're our finite zeros and pole positions that we can get from our open loop transfer function. So putting this in, we had a 0 at -6. So this is going to end up being a double negative, so it becomes +6. And then we have 3 poles that we need to put in here. So we had 1 at 2. It's a sum of, so we add on. We then had a pole at 4 and another pole at 9. So this equation here is really ugly to try and solve by hand because it ends up being a polynomial, and it's going to be a third order polynomial, so it's a bit messy. So what I'd recommend is, in this situation, go ahead and put it in Matlab or Wolfram Alpha or your calculator to be able to solve it. So I've put it in Wolfram Alpha. This is it, and it's given me 3 different solutions to my problem. So I'm going to need to go ahead and figure out which one is the one that makes the most sense. So let me just put these down on our paper, our 3 solutions. Okay, so looking at these, only one of them is actually going to make sense. So before, up here at step 3, we concluded that we need 2 infinite zeros, and they need to join to our poles at -2 and -4. So we can see that these are joined along the real axis. So it only makes sense that our breakaway point can sit on that axis. So 2 of the solutions that we just solved for actually had imaginary components. So they'd be sitting up somewhere off the axis, and doesn't make sense. So we need to pick the real number that's between -2 and -4. So if we pop that back down, this is the one that's going to make sense. It's between -2 and -4 on the real axis. These ones don't make sense, so we can discard them. So let's go back up here and mark in. So we'll say about here is our -3.09. So that's where it's going to break out of our axis. So we should be able to complete the root locus now. So when it breaks out of this axis, it needs to break out at 90 degrees up and down. It's then going to try and approach this straight line asymptote, and it gets closer and closer to it until it actually touches it at when it reaches infinity, positive infinity and negative infinity. So that's my best job of drawing it manually. If you want to, you can try and compare against the Matlab one, which we'll do in a second. So there was one last step to our process for drawing these root locus diagrams, and that was to find the imaginary axis crossing. Now we can actually look at this root locus diagram and see that at no point is any of the root locus coming across this imaginary axis. So therefore there's no point trying to compute where that happens, because you're not going to get an answer that makes any sense. So this is our complete thing, and let me just mark down the bottom here. Step 6. We've got no imaginary axis crossing. Alright, so let's compare my solution with the Matlab one, because Matlab's obviously going to be able to draw it much neater than me. So that's ours. If we have a look at Matlab, this is the code that I wrote to be able to look at it. Just remember that you're looking for the open transfer function in here, and you don't put the k inside your transfer function for Matlab, because when you plot your root locus, Matlab's going to do that for you. So this is what it plots, and where these lines move, that's telling you where the poles and the zeros are going to go as you change your k value. So we can double check our values that we got. So one of the critical points that we saw was the breakout point for our root locus. So if you drag your point down here, you can see this is as close as I can kind of get to where the breakout occurs. And we can see it's at -0.3909, sorry, -3.09. For the real component, this is almost 0, so it's pretty much on the spot. And that agrees with what we calculated for the breakout point. So the other thing that we can look at is what value our two branches here approach, because that's going to be the asymptote line. So if we go as far as we can on this diagram, it approaches negative 4.47, and you can see it's still got a bit of a curve, so it hasn't quite flattened out completely. So it's probably within expectation that it will approach that 4.5, get a little bit smaller as it goes toward infinity. So that would confirm our theoretical calculation, where the asymptote vertical line here is at negative 4.5 crossing the real axis. So I think that's the only major points of interest that we can confirm on this root locus diagram. But in other cases, you might be able to confirm the imaginary axis crossing and so on. So that's all there is for this video, and I'll see you in another one.